let's talk about Chapter 5. In this one, we're taking things that we talked about in Chapter 2 and in Chapter 3, the descriptive statistics, and then we're adding in the stuff we just talked about with probability, kind of putting those two concepts together to get probability distributions. So a probability distribution is going to describe what probably will happen instead of what actually did happen. And we usually put these in a table. We can also represent them in a graph, sometimes with a formula, although we won't do much with formulas here. So before we can talk about probability distributions, we do have to talk about one other concept, and that's the difference between that's the concept of a random variable, which is just a way of representing a different outcome for an experiment. And we have to be able to tell the difference between discrete and continuous random variables. So these are two terms that we need to talk about. And this chapter, Chapter 5, we're going to be talking about discrete random variables and discrete probability distributions. But we'll look at how to tell the difference between the two. All right, so what we're going to talk about is the concept of random variables, how they relate to probability distributions. We'll look at distinguishing between discrete and continuous random variables. We'll look at some formulas to find the mean, mostly, for a probability distribution. And then we'll determine whether outcomes are likely to occur by chance or whether they're unusual, meaning that they're not likely to occur just by chance. Okay, so first of all, a random variable. We usually use X to stand for a random variable. This is something that has to have a numerical value, and this is just one of our outcomes of a procedure. So the important part here is that a random variable represents an outcome with a numerical value. And a probability distribution basically lists every possible outcome numerically. So it lists all the values of your random variable, and then it gives the probability for each one. Now when we talk about discrete and continuous random variables, discrete is what we're dealing with in this chapter. Discrete means that we have a finite number of values, that they're countable. In other words, we could look at them and count how many there were. Or at least we could start counting. We might have an infinite number of values, but it's something that we could start looking at the list and counting 1, 2, 3, 4, and so on. If we have a continuous random variable, on the other hand, this would have infinitely many possible values where it's not something that you could count. So for example, this would give us a continuous random variables would have a whole range of possible values, not just 1, 2, or 3, but every possible real number between 1 and 3, for example. Another way to think about discrete variables is that there are gaps in between. Continuous variables don't have gaps. Okay, so for discrete data, again, this is when we have a finite number or a countable number. So for example, if we started out writing a list 0, 1, 2, 3, and notice that how there are gaps in there. Some other examples of discrete data, how many cars a car dealership sold last month. So let's say they sold 89 cars. That would be discrete. And the number of possible cars they sold would be a discrete variable. The number of students enrolled at LCCC each semester. This is something that we'd be able to count. The year that I graduated from high school. That could be 1951, it could be 1972, it could be 1989, it could be 1994. But it couldn't be anything in between one year and the next year. So for example, it couldn't be something like 1994.1 because that wouldn't make any sense. So there are gaps between the values. But for continuous data, again, this is something where we have a range of values. There are no gaps or jumps in it. The easiest way to tell that you have continuous data is if it's something that's measured, like a height, a weight, a temperature, or a time interval. So for example, 16 seconds, that kind of thing. Here's an example. The actual contents in ounces of cola in Coke cans, labeled 12 ounces, is continuous, since the actual contents could be anything in a whole range of values. If they made a mistake and didn't fill the can at all, it could be 0 ounces, or it could be anything up to, from that up to the maximum amount that a can will hold. And since this is a measured value, Technically, it could be anything within that whole range. Some more examples of continuous data would be things like the amount of time it takes each student in the course to complete our first exam, or the height of a 3-year-old elm tree, the weights of 59 babies born at UMC last month. And here again, note that the weights are continuous, but the number of babies here would be discrete. Now let's talk about graphs with probabilities. If we have a probability histogram, this is really just like a relative frequency histogram. The only difference is that the vertical scale is going to show us probabilities. So notice in this one, in this graph, we have different possible outcomes for the number of Mexican American jurors among 12 jurors. So that number could be anything from 0 up to 12. So these are all of our possibilities. And for each one, we have a probability represented by the height of the bar on the graph. So notice the one with the highest probability would be that we get 10. Now the requirements for a probability distribution, number one is that if you add up all the probabilities in a probability distribution, they have to add up to 1. The other one is that every value in the probabilities column has to be something between 0 and 1. It could either be a 0 or a 1, but in other words, it can't be negative and it can't be greater than 1. So let's look at this one and decide whether this is a probability distribution or not. So notice we've got our x, which is our random variable. We've got all of our possible outcomes listed here. In this case, the possible values for x go from 0 up to 5. And for each one, we have a probability listed. So this looks like it could be a probability distribution. But it also has to meet those conditions. If we look at these probabilities, they're all between 0 and 1, so we're okay there. But if we add these up, they add up to 1.168. They do not add up to 1, so this is not a probability distribution. Now, some formulas that we'll use with probability distributions, though truthfully we're only going to use this one, so you can ignore the rest of these formulas. So we are going to use the one for the mean, and it's actually not that hard. The easiest way to do this is by using a table. If you already have your probability distribution in a table form like this one, then to find the mean, what you're going to do is add another column. So we're going to add this column, and in this column we're going to take each x and multiply it times its probability. So in this first one, that gives us 0 times 0.13. Multiply those two, that gives you 0. If we do this for each one of these, then we get all of these results. So if we just keep multiplying across, then once we've done all that multiplication, then we're going to take these results and add. Okay, so if we add all of those results that we got, that adds up to 1.62, and that's our mean. So we're done. So basically, you just multiply across, then you add, that gives you your mean for your probability distribution. And the round off rule for any of our statistics here, for mu, sigma, and sigma squared, or in other words, the mean, standard deviation, and variance, is that we carry it to one more decimal place than we had for our random variable. So, as in the last problem, if our values are integers, then we're going to round these statistics to one decimal place. We already talked about this range rule of thumb a little bit in the last unit. This says that most values should lie within 2 standard deviations of the mean. So an unusual value in this book is if it's outside this range, if it's more than 2 standard deviations away from the mean. Okay, and something that we call the rare event rule. If we've made an assumption, like for example, if the assumption that we're flipping a coin that's fair coin, and we have an observed event such as 1,000 tosses of a coin, if the probability of that event actually happening is extremely small, we're going to conclude that our assumption that we made is probably not correct. Now, the mean of a probability distribution is actually just the same as what we call the expected value. So down here, this is why I put this in a box. The expected value is the same thing as the mean of the probability distribution. And what the expected value gives us is the long run average expected value of our random variable. So in other words, if we repeat something a whole bunch of times, like 1,000 times or 10,000 times, what's the average value of the results that we're going to expect? So here's an example. A contractor is considering a sale that promises a profit of $38,000 with a probability of 0.7, or a loss due to bad weather, strikes, and so on, of $16,000 with a probability of 0.3. What is his expected profit? Now what this really means is that if he repeated this type of sale time after time after time, like I said, a lot of times, like 1,000 times in a row, what would he expect to average as a profit for each time he repeated it? That's what the expected value gives us. So to find this, first we need to create a table with our probability distribution. So we need to list all the possible outcomes and the probability for each one. So in this one we only have two possible outcomes. He either gets a profit of $38,000 or a loss of $16,000. And notice that for the loss, we have to put that as a negative value. So that's why this was a minus 16,000 right here. We've got the probabilities that are already given to us. So now for our expected value, or expected profit, we just need to go through and use that procedure we talked about to find the mean, or the expected value. So we're going to multiply across with each one of these. So in the first row we get 26,600. In the second row, notice we get a negative number because our 16,000 was negative. So we get negative 4,800. If we add those two, we get 21,800. And that is our expected, or the contractor's expected profit. Now we're going to talk about binomial probability distributions. These are when we only have two relevant categories, something like yes or no, acceptable or defective, or survived or died. This is when we only have two possible outcomes. So to set up a binomial probability distribution, we have to start with something that we call a binomial experiment, and it has to meet all of these requirements. So we have to have a fixed number of trials. So for example, maybe we're pulling 10 M&Ms out of a bag. That would give us 10 trials. The trials have to be independent. So in other words, the outcome of one trial doesn't affect the probabilities in any other trials. For each trial, we can only have two possible outcomes, and we usually refer to these here as success and failure. And last of all, the probability of a success has to remain the same for each trial. Now what this usually means is that we sample with replacement. In other words, if we pull an M&M out of the bag, we write down whether it's red or not, we put it back in the bag. That way the next time we have the same exact number of M&Ms in the bag as we had in the first trial. Okay, in our notation, success and failure are our two possible outcomes. We're going to, for each one, we're going to define what success is and what failure is. We're going to use a small p to stand for the probability of success on any one trial, and q will be the probability of failure on any one trial. All right, so we have our notation. N is the number of trials. X, usually we use that to stand for a possible outcome, so this could be any specific number of successes in our N trials. So for binomial distribution, this can be anything between 0 up to N. Small p is the probability of success in one of the N trials. Q is the probability of failure in one of the N trials. And the probability of X, and notice that this is a capital P here, is the probability of getting exactly X successes among the N trials. And exactly is an important word there. A couple of hints for doing binomial distributions and probabilities. Make sure that the X, which is the number of successes, and the P, which is the probability of success in one trial, both refer to the same category. If you only have two categories, make sure that they're both referring to the same one. And it is possible to sample without replacement if you have enough values in your population. So, for example, if we're sampling out of the whole United States, we're not going to worry about sampling with replacement because the difference is too small to worry about. Now we'll talk about two different ways to find binomial probabilities, but please notice that we're not going to use the binomial probabilities formula in the book. It's just too complicated for us to spend time on, especially when we have technology that we can use. So here's the first method that we're going to talk about, is using technology. With StatCrunch, you'll actually be doing this in Tech Assignment 2. So this is just a screenshot of what it will look like in StatCrunch. Notice that you put in your N, put in the P, and then you put in an operator and an X, and you click compute, and it'll give you your probability. Now this one over here is using a TI-83 or 84, which is really easy. You find the function called binomial PDF or binomial CDF, and you put in the N, the P, and the X. So that's how the order of that goes. You've got N, P, and X here. And we'll talk about the difference between these two in an example that we do. A third way you can do this with technology is to use Microsoft Excel. It has a function, again, that will find this for you. And in this one, I tend to get confused because this is in a little bit different order. In this one, you put in X, and then N, and then P. And then you put in either a 0 or a 1 to tell it whether you want cumulative or not. But we'll talk about that later. The other method that we can use, and that some of you will need to use on your tests if you don't have a calculator that'll do this for you, is to use a table. So I put a little bit of a table in here. This table is available in your book and in Course Compass under Tools for Success, and I'll also put one out on Angel that you can use. So in this one, for example, if we had N equals 12 and P equals 0.80, then our probabilities for these different values of X, for X being exactly 4, the probability would be 0.001, and so on. All right, so let's use a couple different ways to find the probability of exactly 5 successes if we have 12 trials and a probability of success on any one trial is 0.20. First, we could look in the table. We'd look under N equals 12, X equals 5 in the P equals 0.20 column. And if you look that up, you'd get 0.053. And then we could also use StatCrunch. So here's our binomial calculator in StatCrunch. We'd put in our N here, the P here, the X here, and because we want exactly 5 successes, we put an equal in here, and this would give us 0.053. Okay, this is one place where you do get to use a couple of these formulas. We'll use the mean formula and the standard deviation formula. Oh, whoops. And we're actually using these because they're actually really easy. So remember here, n is the number of trials, p is the probability of success, q is the probability of failure. So for your mean, you just take and multiply n times p. For your standard deviation, multiply n times p times q, and then take the square root. Pretty easy. Let's do an example overall with our bag of M&Ms. So first, this is the same bag that we talked about before. Our procedure is going to be to select 10 candies from the bag with replacement. In other words, we're putting the candy back each time before we select another one. And each time we pick one out, we're going to record whether it's red or not. So at the end, we'll have a result of how many candies out of the 10 were red. So first question, is this a binomial experiment? Then if it is, we're going to find p, q, and n, and we're going to find the mean and the standard deviation. So for the first question, is this a binomial experiment? Well, there are only two outcomes, because it can either be red or not red, because that's what we're recording up here. Since we're replacing the M&M each time, because it says with replacement, that means the probability is going to be the same for each trial. We do have a fixed number of trials because we're selecting 10 candies. So yes, this is a binomial experiment. Next question, we want to find p, q, n, the mean, and the standard deviation. So p, we actually figured this out earlier, would be the number of red candies out of the total in the bag. So that's 12 over 103. Q is going to be 1 minus that because they're actually complements of each other. So this would be 1 minus 12 over 103. So it's 91 over 103. And our n is 10. Now for our mean, we just take n times p, so that's 10 times 12 over 103. That gives us approximately 1.165. And remember, we said that we're going to round to 1 decimal place more than what we have in our data. Since our data was all whole numbers, we're going to round to 1 decimal place. For our standard deviation, we take n times p times q. So we multiply those three together. This is approximately 1.029315. Now I notice I didn't round it yet because we still have to take the square root. So if we take the square root of that, we get 1.015. Now we can round to 1 decimal place. Let's do a couple more problems with this setup. Since we know this is a binomial experiment, we can use our binomial functions to find some probabilities. So the probability of getting exactly 2 red M&Ms, or getting less than 3 red M&Ms, or getting at least 7 red M&Ms. And these I showed how to use your TI-83 function to do this. You can also do this with StatCrunch, Excel, or a table. Okay, so the first one, exactly 2 red M&Ms. For exactly, with your calculator, that means that you're going to use the PDF function. That gives you one exact answer. So, and you're going to put in the n, the p, and the x, and our x is 2. So I'll actually let you do that on your calculator if you have one, or you can use StatCrunch. Now for the second one, less than 3 red M&Ms. Now this is where binomial probabilities get a little bit tricky because you have to figure out exactly what numbers you're including. Less than 3 would mean either 0, 1, or 2 for possible outcomes. And notice in this one you're using your CDF function. Because that will automatically go from 0 up to whatever number that you put in. So in this one we put in the n, the p, and the x, and it will automatically give you the whole value from 0 up to x. And for the third problem, if we're getting at least 7 red M&Ms, at least 7 means 7, 8, 9, or 10. Because our binomial CDF function does a less than, we have to use our complement. Our complement of 7, 8, 9, or 10 would be from 0 up to 6. So we can find that and then subtract that answer from 1. So here would be the whole thing that we would do. We'd take 1 minus our binomial CDF, we put in our n, p, and x, because we want to go from 0 up to 6, we'd put a 6 there. And that would give us our final answer for the problem. Now finally, when we're interpreting results, since we know how to find mean and standard deviation for a binomial probability distribution, we can talk about maximum and minimum usual values from that range rule of thumb. In our M&Ms example, since we found our mean right here and our standard deviation, that means our maximum usual value would be 1.2 plus 2 times 1.0, or 3.2. Our minimum usual value would be 1.2 minus 2 times 1.0, which would give us a negative 0.8. Since in that setup, the minimum value that we could get anyway would be a 0, we couldn't go below that anyway. So in this case, if we got 4 or more red M&Ms out of the 10, that would be considered an unusual result, because the 4 would be larger than our maximum value right here.